Hi! What is SSB in our ham radio world? And what is a balanced modulator? And where do we need a balanced modulator for? And how does a balanced modulator work? We want to try to bring some light into the dark, shall we? Okay, let's give it a try. So even on older radios we find modes like, now let me go a little closer here to the relatively old icon, and even there we find modes like LSB and USB, which stands for lower sideband and upper sideband. And well, this is also a very old radio, and I can use the mode button, and you see I can find upper sideband and lower sideband, and of course I can find AM. So what is it all about? Well, let's start at the beginning. It all starts with amplitude modulation, with AM. And well, all the older OMs may remember, or they certainly remember, on amplitude modulation as standard modulation on shortwave. So it is a very nice and stable modulation mode, and it is still a very common modulation on commercial broadcasts. So it still works fine, but in the amateur radio world we was very fast searching for other solutions, and therefore we find SSB, which is nothing else than single-sideband. And as the word already tells us, single-sidebands, we are talking about one of the both sidebands, so the lower sideband and the upper sideband. But what is it? So we may understand what is behind single sideband and AM, and how hangs it together. So let's start with a carrier, and let's try to develop what's happening step by step. Well, to understand it all a bit better, I've set this old radio to AM modulation, and well, we want to show now onto our spectrum analyzer how the carrier looks like without any modulation. Okay, so here is our spectrum analyzer, and I have set the center frequency on 14195 megahertz, and that is where the radio is dialed in. And as I said, without modulation I'm now pushing the PTT, and yeah, that is exactly what we can find. So we see here our carrier. Well, and to see it a bit better, I will now change here my parameters, and what we can see, I mean, I have a span here of 50 kilohertz, which is much too big, so I'm gonna reduce my span, let me say, to 10 kilohertz, and then we see really a nice carrier without anything else. So this is only the high frequency carrier without any modulation, so without any speech, if you like, on it. And what we want to transmit is not only the carrier, it is at least our spoken voice. So that is what it is all about. So I made now the picture a little bit more narrow, so that we really could see what is happening beneath our carrier. I mean, what you can see here, it is not really the cleanest oscillator which is producing our HF signal, but that is another story, so we don't want to look into it today. But what we want to look into is where are the modulation products. So as I already said, now the span is 10 kilohertz. So from here to here it is 10 kilohertz, and that means one unit is 1 kilohertz. So that means, yeah, let me put our marker onto it, and you can see it is approximately 14.195 megahertz. So that is dialed in frequency, and yeah, we see the carrier is exactly on that frequency. And if we would bring a modulation to the microphone input, then we should see this tone which we want to transmit. So therefore we should then see, let us take the example with 1 kilohertz. If we want to transmit 1 kilohertz, then we should see here another carrier or another tone, however you want to call it, and that is then the signal where our audio frequency is mixed into it. All right, so that is what we want to transmit. Okay, and again, this is our carrier on 14195 megahertz, and now I want to modulate this signal with 1 kilohertz audio frequency, and that is what I'm now doing. Now this carrier is modulated with a tone of 1 kilohertz, and what we can see here is exactly our 1 kilohertz tone beneath our carrier. And we see as well a second point. So we find the same 1 kilohertz tone beneath, twice beneath our carrier. So it is at least our upper sideband and our lower sideband. So this is telling us a little bit more about how it is working. And of course, a modulator is nothing else than a mixer. And we know already from a mixer that a mixer, due to his technique, it is producing a plus mixing product and a minus mixing product. So that is what is always happening when we have a mixer process ongoing. So, and that is exactly the same with our modulation. So modulation is as well a kind of mixer, and therefore we have of course these two products. So these are the both mixing products, and therefore we get the upper sideband and the lower sideband. And you see, okay, we have still our carrier, and we have our both tones. I mean, it is the same content. Here we have our 1 kilohertz tone, and as well on the lower sideband. So the audio content is exactly the same. So we really could use well, both, or we can use the upper sideband and the lower sideband, and then we have exactly the same audio information on our carrier. And of course there are some additional information here in our shown picture. I mean, the sidebands are also telling us something about the audio volume level. So if we are modulating the carrier with a higher audio gain, then these sidebands are getting different. So in our case, so we are increasing the audio gain, and we can see I'm just increasing the audio gain, and you have seen the jump in our sidebands. So let me do it again and again, and it takes a while because, you know, the sweep time is where is it, 2 seconds. So it takes a while until the information is present here on our spectrum analyzer. And if I decrease the audio level, you see now our sidebands are dropping. So that is nothing else than the information about our audio volume gain, if you like. And well, I also can switch it to 0, and then you see now the audio is gone, so there is only the carrier left. Okay, and what gonna happening if we change our audio frequency? As we said before, this is exactly 1 kilohertz. So if I go now and change our audio frequency, let's say I go to 1.5 kilohertz, then you can see that we now hear exactly 1.5 kilohertz away from our carrier. And I can go up to, let me say, 2 kilohertz, and you see now our sideband exactly on 2 kilohertz. And let's go to 3 kilohertz, and you see now we are moving out, and we will have exactly the same when we go down with our audio frequency. So this is again 1 kilohertz, and of course we have lower frequencies in our audio voice as well. So now it is 500 hertz, and you can see that the audio information is going closer to our carrier. So that is what it is happening with our AM, our amplitude modulation. Well, and as I said before, amplitude modulation is still used on AM broadcasting stations. I mean, here in Europe we are closing down all AM stations. We only have FM stations. But anyway, there are a lot of broadcasting stations in the world who are using the AM mode. So there is basically nothing wrong with it, because it is a very stable mode, and yeah, it is used, as I said, all over the world. But well, there must be a reason why all the engineers were looking to another mode. So why did they look for another mode, and why did they develop SSB, single sideband? So that is the question. And well, again, if we look onto this picture right now, we have a 3 kilohertz tone here on our picture. And well, what you can easily see is to transmit this AM signal, we need a bandwidth of 1, 2, 3, 4, 5, 6 kilohertz. So to transmit a signal which is carrying only a 3 kilohertz tone or a 3 kilohertz audio information, you always need 6 kilohertz bandwidth, and that means this bandwidth is needed within our entire bandwidth which is available on the respective band we are working on. And subsequently that means that if you always need, like in this example, 6 kilohertz, that means that there is a limited number of stations who can work side by side. So therefore in I don't know exactly when it started, but it must be the middle of the 30s or somewhere in the 50s when they started to develop single-sideband, because as I already said, single-sideband means there is only one sideband which is needed. So for instance, we know that all informations are already here in this component. So there we have our carrier information inside and of course our tone. So why not only transmit this component? And well, you know, where do we need the carrier for? I mean, the carrier at least is consuming a lot of power, and the second sideband is also consuming power. And if we would find a solution to suppress our carrier, then we would simply have more energy for our sidebands. And if we would be able to suppress as well the second sideband, which we don't need, and it doesn't matter if it is the upper sideband or the lower sideband, then we only would need a bandwidth of maximum 3 kilohertz, and that means we would get the doubled numbers of stations theoretically on the same band. So that is very important, and in the early days of amateur radio there were really a lot of stations, and well, you know, all the engineers were looking for a solution to get more stations on the band. So therefore they were looking for a technique which is consuming less bandwidth, and therefore if we only, you know, transmit one sideband, then we really have only, like in this example, 3 kilohertz which needs to get transmitted, and not 6 as it is here in our example. And that was then you know, the basic start-off point to develop single-sideband. Well, and that is what single-sideband is all about. So we just try to get this components away, or maybe this components away, and we only then transmit, in this case, our lower sideband, and in this case we only transmit our upper sideband. And therefore exactly therefore to get away our carrier, we need the balanced modulator, because as I said before, we need to get our audio information onto the carrier, and therefore we are using a balanced modulator to get, of course, our audio information on the HF component, but on the other hand we want to reduce our carrier, and that is what our balanced modulator is for. So we want to look a little bit more into the technique of a balanced modulator. We want to see how it works, and then we may better understand how it plays all together. Shall we? Okay, so let's draw a balanced modulator, and let's build it, and then we can do some experiments with our balanced modulator, and we can then find how it works. Well, what you can see here is one of the easiest balanced modulators which is on the market, and which will work finally. Well, what we have is that we have here our HF input, or well, also called local oscillator, or support carrier, or whatever we want to call it. And we have here our microphone and our audio amplifier. And well, the most important part is the broadband transformer, and this here in the middle is our broadband transformer, and then followed by these both diodes, and then we can really pick up our, in this case, double sideband signal. So that means this little circuit will be able to suppress our carrier, and that is what we want. So that is what we discussed already on the spectrum analyzer picture. We want to suppress our carrier, and well, carrier, let's draw it here. So we have, as we have seen it here in the middle, our carrier, and then we have right and left our upper and lower sideband, and we want to get rid of this carrier here. So we try to reduce it as much as possible, and therefore we need our balanced modulator, so BM, right? And well, first what we need to do is produce our broadband transformer. Well, and it is very important how our broadband transformer is wounded or twisted up. So that is something what we need to consider, that this circuit can work in the right way, and therefore we put a dot always here to our transformer, and this dot is indicating where you know this twisting starts, and that is very, very important that this model can work. Well, so as I said, the function is depending on how the quality of our broadband transformer is, and secondly it is depending on the diodes. So they really should be exactly similar, so they should be really equal. And the broadband transformer should be really the best you ever can get, and then you may have the chance to reduce the carrier to the max. In our case, we can be happy if we will be able to reduce our carrier, let me say 35 or 40 dB, and that would be really great if we are possible to achieve something like that, because normally, you know, nobody would do it these days like I have wrote down it here. So we have very modern integrated circuits to do this job, and normally this would be done with 4 diodes. So that is the reason why this little circuit is also called ring modulator. So, you know, this is just an example to understand why we are able to suppress our carrier, and therefore now it is not our highest priority to reduce this carrier really to the max. It is just to show how it works. Well, and as we want to produce it all by ourselves, and as this diode will be not equal, we will have not that phenomenal result, but after all, we will be able to show how this circuit is working. So therefore we need a core like this here, and on this we want to wind some, you know, of this wires here, right? And as we need at least 1, 2, 3, we will twist 3 wires together like so, and then we drill it as much as we can, and then we will have what we need to put it here on a core like this. Yeah, and what you can see here, I've already twisted these 3 single wires together. So let me see if when I go closer, if you are able to see it through the camera, maybe a little bit. So yeah, this is now really twisted together, and well, I think it is reasonable, so we can use it. And now we have to put it on our little core. Yeah, and we really can do it by hand. So that is now pretty simple. But remember, if I put it through this hole here, this is already one wounding, right? And we need, I don't know, approximately 15 windings here through the core, and you know, that works like this here. As I said, we really can do it by hand. It is a little bit complicated here through the camera, so that is the challenge, not not to get it here on the core itself, so that is not very difficult. So you can see now you go around and around and around until you have 15 on the core, and then you have finally a nice broadband transformer. So that is how this basically works. I will now finish this little broadband transformer, and yeah, we need to build our circuit here on a board like this. And well, I've already taken out this little diodes here, so nice little BAR28, so this will work for our circuit. And I have tried to find two similar diodes, so that is not really easy, so there are differences, but in any case, we will be able to reduce our carrier as I've shown it down here. Even if we are not able to have really equal diodes as we should need, and if they are a little bit different, that always mean that the performance of this reduction here is getting worse. But anyway, so that is not our problem of today. We just want to show how it works. And of course we will not able to build the best broadband transformer by hand, but again, that is not really the problem. Okay, and as I said before, basically this is a mixer, and a mixer always means that we bring two frequencies together to get a new one. So a mixer looks in a schematic like this, and we have here an input, and we have here a local oscillator, and then here we will have our IF intermediate frequency. And basically it is the same with our balance modulator, because what we want to get out of it is this here and that. And that is exactly what I have told you before. So let us assume that we have a local of 14 megahertz, and in our case our audio frequency will be 1 kilohertz. So that means we expect our intermediate frequency should be a mix of this both. So that means it is the plus product is 14.001 megahertz, and the minus component will be 13.999 megahertz, and that is exactly the upper and the lower sideband, and that is what we expect as outcome. So this is not really different from a normal mixer, and I do not want to go into the theory of a mixer today, so that is completely a different story. For us today is to understand that it is basically a mixer, so we get the plus and the minus component, what a normal mixer would do as well. But the balance modulator will, as we already said, something additional, so it will reduce our carrier, because as we said, we don't want to have it in our transmission, because our carrier will consuming energy, and we better want to have this energy for our sidebands. and yeah, therefore we just simply want to reduce it, and this balance modulator will do it. Okay, and well, now we need to consider what is gonna happening if we feed in here the local oscillator, so the high frequency, the carrier, the supported carrier, whatever we want to call it. And in our example we said it is our 14 megahertz, but it you know, it is depending on the circuit itself, so it must not consequently our 14 megahertz. So it depends on the circuit which was developed before. So therefore this is only an example. But anyway, so let's assume we start here with a negative half wave. So that is the first. So this is our zero line, if you like, and this is a negative half wave. And now this twisting scheme come into our game. So if we start with a negative half wave, and of course there will follow a positive as well, but just to understand what happens, we want to go through like this. So yeah, we start with a negative half wave, and you know, it is twisted as I've shown it here. So that means that at this point here we will have a negative half wave as well. And as you know, in the middle, this both wires here so are twisted together, and you know, we are feeding in our audio frequency just into the middle, but that is now a different story. Our local oscillator, or our high frequency component, will be available at this bottom point here of our broadband transformer as well, and therefore we will here will be a positive half wave, because you know, a coil always is able to shift the phase, and that is happening here, and that is a beauty what you can do with a coil. So you always are able to shift the phase, and you know, when I start with a negative half wave, and it is twisted like it is in here, and if it is wired as we have shown it here, then we have really a phase shift here on this, and this phase will follow the input phase. And that means if you know, we start with this negative half wave, we will have a negative half wave here as well, and the negative half wave here is able to open this diode, right? And on the other hand, the positive half wave here is able to open this diode. And that means, you know, at this point we have then, again, if you like, here the negative half wave, and here the positive half wave. And now this both half waves gets summed up in this resistor, and can be picked up and measured here, of course, at this coil. And that what is now happening here is very interesting, and therefore we want to do a little experiment. Yeah, okay, let's do some experiments, and well, I'm simply phasing in two signals here in our oscilloscope, and yeah, you can see here our first signal, very easy. It is 500 kilohertz, so it's just an example, nothing special. And I have a second signal. It is exactly the same. It is also 500 kilohertz, and both have 500 millivolt peak amplitude. And yeah, I've just put it a little bit like this, that you really see these both signals. And well, we are basically interested in the question what will happen if this both signals gets summed up. Okay, as I said, we want to add up this both signals, so that means A plus B, so signal or amplitude A plus amplitude B. And how does it look like? So therefore I go and match this both signals, that you think it is only one signal, but as we know, it is just behind it, so it vanished here a little bit. But for us, it is clear we have here definitely two signals. Okay, and now we want to use our mass function a plus b to show what's gonna happening if two signals get simply added. So therefore I'm now switching on my mass function here on the scope, and here it is. So what you can see is that now this both signals, so let me see, no, this is now the offset I'm working with. So just to see it again, I have still here our two signals, and this here now is the sum of this both, and that is basically very easy. If we have one sign and the second, and these signs have each 500 millivolt peak, then it is clear that the sum of this both will be in this case 1 volt peak. So it is exactly doubled. So that is what has happened here, and yeah, so that is what is happening or would happening in our circuit as well, if we would have. So let me go here, let me zoom out a little bit. So that would happening if we would have here, you know, on both sides, you know, for instance, a positive half wave, you know, then this positive half wave would get summed up like we can see it here on our scope. And now we want to show what's gonna happening if we are starting to change the phase. And yeah, look what we can really see here now on the scope. You see that the phase is moving out a little bit, and I will now increase it, and you watch simply here our function, our a plus b function, and what is happening when I shift the phase more and more. So you already may recognize that our function here is dropping down a little bit, and now I am exactly on a phase shift of 90 degree, and that is what you can see here, our both fundamental tones, yeah, let me call it like that. And when I now move forward and forward, you see that our resulting signal here, our function, is dropping down more and more. And when I have finally reached 180 degrees, and now I'm on 170 degrees, so you see a positive half wave and a negative half wave are, you know, matching up more and more, and you see what is happening to our resulting signal. And now I'm at exactly 100 degree, and 100 degree phase shift means that, you know, the positive and the negative half wave are eliminating themselves. So that means the resulting signal is exactly at 0, and that is what you can see here very nicely on the scope. And when I now go and change again our, you know, phase, you see as closer I'm coming back to 0, as more signal amplitude I have here at our added signal, right? Our function A plus B. So that is what we see. And yes, once again, let's shift our phase once again until we reach 180 degrees, and then that is exactly the situation we have in our balanced modulator, and that means that finally our local oscillator component, our HF, or our supporting carrier, whatever you want to call it, is gone. And that is exactly how our balanced modulator is working. And now most likely you are able to explain it to yourself what's gonna happening here. So we really have a positive half wave and a negative half wave here at our resistor, and both gets summed up, and as they are with a phase shift of 180 degree, so that means that our 14 megahertz, which we are feeding here in here in our example, will be reduced to nearly 0, and that is what will happening. And now you may imagine, if these diodes are not exactly equal, and if our broadband transformer is not perfect, then we will not be able to get, you know, at least the same voltage levels, and we may have a little phase shift still, so that we are not 100% able to reduce our carrier to 0, as we have seen it here on the scope. So there it was really 0, and that is clear because our voltage levels was exactly the same, and the phase shift was exactly 180 degree, and therefore it is clear that in our example on the scope, our resulting signal or our resulting voltage was 0. Okay, so well, I hope now you have a little bit understood how this is working. So now let's go and build our test circuit, and let's see if everything we have discussed here on our circuit and what we have seen in our little experiment on the scope will really happening in our or with our test circuit as well. Okay, and here is our test circuit. So it is boring to do it on camera because it is simply you know, soldering these components together, but you see really the important point. So that is here our little broadband transformer, and yeah, if you look here a little bit more in detail, you already see that you know, it is not all the same distances, so you know, there are some weaknesses already on how I have twisted it. So well, okay, and as I already said, here you can see our both diodes exactly soldered in, as we can see it here on the schematic. And well, here is our pot where we then will finally have our two signals. And well, here is our audio input. So in our case, we want to test it with 1 kilohertz audio tone, and this here will be our HF input. So I don't know, let's try it with I don't know, 7 megahertz or 3.5 megahertz, so that doesn't matter. It is just to see what's really gonna happening on our HF signal. Is it still available here at our double sideband output or not? So that is what we are really interested in. Does a circuit like this really work, and does it what we want, and that is reducing our carrier as much as possible? Okay, let's give it a go. Okay, so setup is ready, so all is connected. Here is our double sideband output, here is our local oscillator, and I'm operating it currently with 3.5 megahertz, but as I said before, that does not say anything. And here's our audio input with 1 kilohertz. So I'm just simply taking the frequencies here out my little wave station. So you see here 1 kilohertz, and when I switch it to the other channel, so you may read it is 3.5 megahertz, and that is what I'm simply feeding into the balanced modulator. And now let's see what we can get at the output, and therefore we are going back here to our spectrum analyzer, and oops, and now I'm switching on our input signals, and here are our input signals. Or yeah, let us do first this. So this is here of course our carrier. So when I go here onto peak, you can simply see it is really 3.5 megahertz. So now I'm adding our tones, our 1 kilohertz audio tones, and what you can see is that yeah, our carrier is suppressed a little bit, but it is by far not that what we expected, because yeah, if we put maybe a delta here on this both components, so you see that I can't read it because our second sideband is somewhat in between or on it, so well, it is I don't know, something around 20 dB, but it is by far not what we would expect. And well, as I said before, when we go back here to our circuit, we have here our pot, and that should bring us the best balance as possible. And therefore I'm gonna turn now, and we want to see if we are able to get a better balance here into our circuit. So remember what we really need to get it in a good balance. So we need you know, our 180 degree shift, phase shift, and we need of course the equal level. Then it can work. So therefore I try to turn it in, to trim it in a little bit, and therefore let me go back here to our analyzer screen, and now I start turning. I mean, we have a sweep time of, what is it, 1 second, so yeah, it will take a while. And yeah, I'm turning, I'm already turning, and you see I'm able to reduce our carrier nearly to now it is going to the other side. So I really need to find the best balance between, you know, our both inputs. And yeah, what you can see here is now we have already a very nice carrier subspression. So I think that maybe I can do it a little better. So it now would take a bit time to get it to, you know, the best balance. But anyway, what you clearly can see now, we have here now our both sidebands. So we are here, our marker is here on the lower, and yeah, let me go here on peak. So now this is taking the upper sideband, and it is 3.5001, so that is really our 1 kilohertz component. And this is then of course our lower sideband, and here in the middle this is now our suppressed carrier, and that is exactly what we want, and that is exactly the function we expecting from a balance modulator. And I can go back here to our pot, and if I now go and bring it out of balance, you see, yeah, I really can increase you know, the carrier, and now the carrier suppression is really bad, so this wouldn't be good. But when I do it here into the other direction, you can see now it is really going down very nicely. So let me change here the settings a little bit, so then we will be able to see a little bit better what the suppression is. So let me go on delta marker, and if I go here with my delta here, somewhere here into the middle, yeah, you see that is really great. So that is much more we expected when we were designing this little circuit. So that means that our broadband transformer seems to be better than expected, and the diode seems to be better than expected. So we are really able to suppress our carrier of about, yeah, it is here -47 up to -50. So that is really a good carrier suppression, so no question whatsoever. Yeah, and that is how our balanced modulator is working. Yeah, and now this is exactly what we have on our screen, and this here is our upper sideband and this here is our lower sideband. And now this little component here is our carrier, and we have seen it on our analyzer that it is down -50 dB, which is really a good value. But now you know, we let me say we want to transmit on upper sideband, and now we just want to get this lower sideband. Yeah, you know, we want to suppress it as well, and therefore we simply put a filter, and I can't really demonstrate it today because I do not have a good SSB filter here, but anyway is something like this here. So this here is our passband, and we know that our 3 or maybe 6 dB points are let me say from 0.3 kilohertz up to 3 kilohertz. Just again, this is only an example, and that means our entire width, our entire SSB bandwidth is 2.7 kilohertz. And you see, if we have now a filter really here on our upper sideband component, then our lower sideband is not any longer in our spectrum. In the spectrum we gonna finally transmit, because you know this filter here is yeah, let me do it this way here, is directly here behind our DSB output, and there will be maybe a quartz SSB filter, right? And it would look like something like this, and then here at the output, yeah, we will definitely have only our upper sideband, so USB, and you know, our other components, the lower sideband and the carrier, is now gone, because we have here really working our filter over it. And that is how it all works, and that is what we can see here on our spectrum analyzer screen. So that's it. We are really at the end of our story, and yeah, I hope this is helping a bit to understand how it works. I mean, yeah, there is a lot of more behind it, and yeah, you should normally go into the mixer theory to understand it all together. But basically this here really is the transmitter pass in a single sideband radio, and that is how it is working. Yeah, and I hope this was a little bit interesting for you. I'm at the end of this video. I think it was already much too long, Sorry for that, and thank you if you're still here and watching it. And yeah, if you like it, please give me a big thumb up for it. And yeah, catch you next time. Bye.